This video is about special right triangles. The first special right triangle is the isosceles right triangle. This isosceles right triangle has two congruent perpendicular legs and two 45-degree angles and a hypotenuse like every right triangle. We're going to look at the relationship between the hypotenuse and the legs of these special 45-45 isosceles right triangles. The first one has two congruent legs, each has one unit, and we'll call the hypotenuse C. So using the Pythagorean theorem, 1 squared plus 1 squared is c squared, or 2 is c squared, and taking the square root of both sides, c is the square root of 2. Okay. Now let's just take the next example. This one is an isosceles right triangle with each of the congruent legs being 2 units. So again, we're going to use the Pythagorean theorem to find out what the hypotenuse C is. So 2 squared plus 2 squared is c squared. 4 plus 4, or 8, equals c squared. And taking the square root of both sides, c is the square root of 8. Now, that doesn't look like any pattern is emerging, but perhaps we can reveal the pattern by using the property of square roots, which tells us that the square root of a product is the product of the square roots. So first we have to factor 8 into 4 times 2. Since those are equal, the square root of 8 is the square root of 4 times 2. But square roots have a special property which allows us to separate this square root into 2. The square root of 4 times the square root of 2. And the square root of 4 is 2. We can simplify that because 4 is a perfect square. So then it turns out that, while c is the square root of 8, another way to write that is c is 2 times the square root of 2. 2 times the square root of 2. And if the leg is 1, c is 1 times the square root of 2. Let's look at a couple more examples. If we go up to 3 units, c squared is 3 squared plus 3 squared, 9 plus 9, or 18. Again, we take the square root of both sides, and the square root of 18 isn't remarkable, but I have this idea that maybe it's a multiple of the square root of 2. So I divide 18 by 2, and the square root of 18 is the square root of 9 times 2. And using that special property of square roots, the square root of 9 times 2 is the square root of 9 times the square root of 2, or 3 times the square root of 2. 3 times the square root of 2. Well, now let's try something a little bit bigger and make the congruent legs be 10 units. Let's see if the pattern still holds true. C squared is 10 squared plus 10 squared, or 100 plus 100, 200. C squared is 200, and c equals the square root of 200. Is it going to be a multiple of the square root of 2? Well, 200 is 100 times 2, which equals the square root of 100 times the square root of 2, which equals 10, the leg, times the square root of 2. And so we see that our pattern follows for every example. In an isosceles right triangle with one 90-degree angle and two 45-degree angles, the hypotenuse is always the leg times the square root of 2. If the leg is 1, the hypotenuse is 1 times the square root of 2. If the leg is 10 units, the hypotenuse is 10 times the square root of 2. And if we don't know what the leg is and we call it x, we still know that the hypotenuse will be x times the square root of 2.